All right, so let's think about a find statement for this problem now. If you read through that, you'll see that it's asking primarily for three different things. One is the time that you need to stop the culture. I'm going to stop. So likely that's when the bacterial population is at the max. And then another thing is it asks what's the pH of the system at this harvest time. And then it also asks for what's the rate that you need to remove heat removal. What's the rate that you need to remove the heat to keep the temperature of the actually it's the temperature to the amount of heat removed to at the end to bring the temperature from 25 degrees C to 4 degrees C. Sorry about that. To chill the system. If you look at the problem statement, you can see here that it says at the very end, you're needing within 30 minutes, you need to remove go from 25 degrees C to 4 degrees C. With the diagram, let's think about the diagram for a second. What is the system in this case? Yeah, it's going to be the fermentation reactor. And uh, do you have any mass going in and out of this system? So I'm not going to draw the system here. It would just be a box labeled as the bioreactor that you're growing this bacteria in. So let's now go to the analyze. First, we need to make assumptions. So we're going to assume now there is one system, it's going to be this reactor, but there are uh, three different systems as far as there's a mass system, there's also a charge system, and there's a energy system. Now, they're all the bioreactor, but that bioreactor we're going to have to evaluate as a mass system, as a charge system, and as an energy system. So the mass system is going to be the assumptions here is closed. You've got no mass coming in and out. You've just got the bacteria expanding and the amino acids already in the system at the beginning. It's going to be reactive. You've got generation of bacteria, you've got consumption of amino acids, and generation of insulin. So, and then it's also going to be dynamic in that the the extensive properties, the mass of each of the items in here, and the pH basically is going to change, and the energy is going to change, especially when you go from 25 to 4 degrees C. So all of these systems are similar. They're basically the closed. It's going to be reactive, dynamic, and then the energy system is still going to be closed. Now this one, however, though, this last moment here, after the reaction's done and you're cooling it off, the reaction is not going to cause any energy changes, uh, and there's no reaction going on at this 30 minutes. So when you're evaluating this system for the energy, this is going to be a non-reactive system. There's not going to be really any input of energy during this here to change the temperature, or the reaction is not going to be significant change for this 30 minutes. So let's go here, but it's still dynamic. The temperature is changing from the beginning to the end. Then we need a basis, and I'll just combine this all with the given data. And if we need any extra data, I'll just stick it in here too. So in here, we're going to have that the initial bacteria at time 0 here is going to be 10 to the 5. We also know that you're given a bunch of these first order and other constants here that you need to record. So for me, K1 would be A for me, let's say it's 2 over 100 kilogram hours. K2 here, this is going to be one that's difficult to figure out from the problem statement, but it's basically going to be used for the insulin production. I'm just going to set up, because we know the bacteria holds this much, I'm just going to, the insulin is going to grow at K1 times basically the mass of insulin that each bacteria has. I need to teach it what a microgram is, so let's do that real quick. Then K3 is equal to C times, well, C for me is, I'll just say it's 2 again, over 100,000 per day, 100,000 per 100,000 days. And then you've got K4 is given, so we need to record the K4. D, let's call it 3, divided by, this is per 100,000 kilogram seconds. Or actually, this up here is 2 milligrams per 100,000 days. K4 is 3. It's actually, I call it D, but I actually didn't say D. This should say D in your problem statement. D times D milligrams. Let's just leave it the way it was. And let's call this, well, that's 3 times 10 to the minus 5, which is 3 over 100,000. And then it's kilogram seconds. And then you've got, what else is given here? K5. I use a K5. There's no K5, is there? Nope. All right. What else is given? Let's see. So now some of the extra things we're going to need. Oh, actually given was the amino acid. Was 1 kilogram to start with. We are given some temperatures. T1 is 25 degrees C. Temperature, degrees C. And then T2 is 4 degrees C. And then some of the extra data you're going to need is going to be the molecular weight of insulin is 5808 grams per mole. The molecular weight of lactic acid is 90 grams per mole. The molecular weight of the amino acids is 114 grams per mole. And I think I gave that to you in the problem statement up here. Oh, I actually even gave you the insulin molecular weight and the amino acid molecular weight. Okay, maybe the lactic acid is the only one that's an extra data. This is grams per mole. Then, now we're ready to calculate. So let's calculate. We put in a text box here for the calculate. here. Drag this down so you can still read it as we're going here. Oh, it doesn't want to. Well, calculate. So the calculate, the mass system is a first order system of mass here. So we're going to have a differential equation system. That's going to be, so we got to put a solve block in. And what are the things that are happening in this mass system? What are the mass things that we need to keep track of? One is going to be the bacteria. So I'm going to put I'll use a big B as, and the initial condition for the bacteria is equal to the, what did I call it here? This here. We also have amino acid is dependent. If you look at it, you can see that the growth is dependent on the amino acid. It says here that the growth of bacteria depends on the amino acid as well. So we need to keep track of the amino acid, and its initial condition is going to be, what did we say, AA here? Yep, right there. And then we're trying to keep the insulin is what we're interested in. And the initial concentration of insulin is going to be 0 because there's no well, there is some bacteria at the beginning, but it's basically the amount of bacteria at the beginning times the amount of insulin that's in the, and that was given as 4.189 times 10 to the minus 7 micrograms. That is the that times the bacteria. Right? Where did the times bacteria go? So the initial number of bacteria times the amount of insulin per bacteria will give you the amount of insulin that's in your batch at the beginning. And then, oops. We also want to know what the pH does because this is generating lactic acid the whole time. So we need to follow the lactic acid and its initial condition. There is no lactic acid at the beginning, so it's 0. So now we need an initial differential equation for each of these now. So the bacteria, if you read up here, it tells you that the that it grows at a first order rate here. Was I not clear about the dependence on the amino acid? If I didn't, we need to change that. That is a first order, or it's actually that makes it a second order. But let's just do it as it reads here. It's a first order, so the amino acid is probably not important then. Let's look at, if it's first order, the differential equation is going to be T B of T is going to be equal to, now the growth is first order on K1, it says here, K with a first order rate constant here of, if it's first order though, this kilogram should be gone. That's not a, that's a second order rate constant with that kilogram written there. So there's a typo in this problem statement. With this, it looks like it's dependent also on the mass of the, so let's just say for now it says second order, and it's dependent also on the amino acid and the bacteria. So let's just write that the way, if it's K1, so it's going to be plus K1 times the amount of bacteria that's in there at any given time, times the amount of amino acid that's there at any time. Now, if it was first order, you would get rid of this kilogram down here and get rid of this here. So if you look at it, K1 is, if it's first order, it's 1 per time times the number of bacteria. So the number of bacteria per time is changing at a dBdt. If it also depends on how much amino acids there, then the amount of amino acids is a kilogram. So then you'd need a kilogram in the denominator of this K1 so that it cancels out the mass from this A here. So let's actually make it a first order and see what happens. I may have some typos because I'm changing things on the fly here, but that's okay. Hopefully it'll help you understand. Oh, undo that. Redo that. Let's call it a first order here. If I do that though, then this kilogram's got to go away. It's dependent only on the bacteria. All right, but it also then says, let's read it as it's rated here. The bacteria produces lactic acid. The lactic acid is toxic to the bacteria, so it dies on a second order rate constant of this, dependent on bacteria and the lactic acid. So this one is going to be a minus because it's dying now of K, was it K what? K3. The bacteria dies by K4 actually. This is K4 times, and it said in the problem statement here, right, that it's dependent on the bacteria and the lactic acid. So this is going to be the bacteria. The more bacteria there is, the faster it dies, depending on the lactic acid concentration. So the more lactic acid and the more bacteria, the faster the bacteria dies. So there's our equation if this is a first order rate here. Okay, so now the amino acid, we probably don't need that if we're going to do its first order here. The amino acid doesn't matter. It doesn't affect the bacteria growth. So we need the insulin here, but the insulin as a function of time is not a difference. It's basically just equal to the number of bacteria at any given time times this same number. However much bacteria is there is going to be how much insulin. Now, if the bacteria starts dying faster than it's growing, then apparently you'll lose insulin, and that's the purpose for here where it says, when do we want to stop it? We want to stop it if you start to actually have conditions in your reactor that start to kill the bacteria, because then you're losing product, you're losing your insulin. So the insulin is going to be dependent on how much bacteria you have in there. So as the bacteria changes with time, then the amount of insulin changes with time. Now the lactic acid is produced, as it says up here, molecular weight, what does it say? The bacteria produces lactic acid on a first order rate constant of K3, depending on the number of bacteria. So here, it's a first order on the number of bacteria. So it's going to be a differential equation, function of time. The lactic acid is going to be dependent on K. What was the K that it said? Bacteria produce lactic on K3. So it's K3. And you have to put this milligram here, which you usually don't see on a first order constant, because it's dependent on the amount of bacteria, and the bacteria is reported as a number and not a mass. If you did it by the mass of bacteria, then you wouldn't need this mass in this term here. That's just to make this K3, when it multiplies a number, which is the times B of T, that doesn't have a unit. So this K3 needs to have the mass per time there. So the lactic acid has a mass per time. So basically it's just saying that each bacteria produces C milligrams of bacteria for every 100,000 days. So that's your production of lactic acid, and nothing consumes it, so there's no minus on this equation. So now you've got your 3 equations and 3 initial conditions. So now we're going to set up the solution solver here. So we need to, there's 3 equations, and we're solving for the bacteria, we'll call it, the insulin, and the lactic acid. It's all going to be equal to ODE solve. And then here you need to have another vector, B of t, this is I of t, and L of t. And let's try just for 30 days, let's say. We may have to change that depending on what happens with the curve. So now we've got a solution here. So now we're going to take this and we're going to plot it. We plot this T times S. And if we look at the bacteria, oh, it's got to be the little b, sorry. The solution is down here in little b. All right, so let's look what it does in days. All right, so those numbers that I had, you can see that the number is shooting up to from 1 times 10 to the 5th up to 1.3 times 10 to the 7 in 10 days. We did for 30 days, so let's see what happens. Oh, so we can see that there's a max at one point, right? When these, and that's probably because there's lactic acid growing at a point where it's going to start killing the bacteria faster than they're growing. So we likely want to catch this right here to stop it. So how can we find that time to stop? Well, one way I did that in MathCAD is to do a solution, to do a solve block, and come in here and do a time to stop. Let's say, let's guess, it's somewhere about 23 days. So let's say 23 days. And I want to know when. The easiest way to figure it out is when this hits a maximum. And so that's going to be when the slope of this curve hits 0. So I just did a test real quick of, I put in a, tested for the derivative here. The solution to the bacteria in this equation here, when this solution, the derivative of this solution turns into 0. So let's make this equal to 0 per day. And then I'm going to find capital time here is going to be when I find the time there. So let's find out what time is. Seconds, I don't want seconds. Let's do 23.8 days. So that peak right there is at 23.8 days. That'll be the time that you want to stop your production so that you can collect the bacteria. And that's the purpose of chilling it here, is to get the growth to stop. So you stop losing, you chill it, and then you collect the bacteria and you collect the insulin from them. But that needs to be done at about 23.5 days here. So then how do you find out what the pH is at the end? And the other thing we have to look at, okay, so let's do the pH now. So now we need to look and see from the solution the lactic acid. So let's plot the lactic acid change. So This one is going to be T times S, and then lactic acid, T times S. So we need to go 0 to 30 days here. So at 23.8 days, 23, that's right here. This is about right there. But that's the time when we want to stop it. So that's going to be tell us the concentration of lactic acid that we need to now use to figure out the pH. So now for the pH, you're basically going to use, if you remember, we're going to take the system, remember that where you do the number of protons in minus the number of protons out plus the number of protons generated minus the number of protons consumed is equal to the number of protons final minus original. And then you do that same thing for uh, A, HA, and then you need your KAP equation, and you need your two net equations. If you remember, the two net equations are basically, in this case, that the number of H generated or consumed is going to be equal to the number of A's generated is equal to the number of HA's consumed, or vice versa, depending on which direction the reaction's going. It could be NHC, NaC, NHAG. This is not your KAP equation. The KAP equation, remember, is KAP is equal to NHF times NAF over NHAF at equilibrium at the end. So now what's happening here, though? You're taking this lactic acid that we're just going to assume that there's an initial pH of the initial pH is, let's say, 7. So that's going to give you an NHF. And now you need to pick a volume for your reactor. And did it say the reactor volume here? Yeah, right here, 10 liters. So then with that 10 liters, and you assume here, what did it give an initial pH? No, well, we can assume it's 7. So then your NHO is going to be, because you know it's 7, is 10 to the minus 7 times moles per liter times the volume. Now the volume I didn't define, so that's got to go up here in this. So 10 to the minus 7. So this is your NHO. Then I'm going to assume that you put in this lactic acid. I'm going to assume it comes in as HA, that it's a weak acid. So the NHA, the undissociated acid, is going to be basically equal to this solution at the time that we solved up here, and then divide that by the molecular weight of lactic acid. How did I do that? La. So of La. And so that's the number of moles of lactic acid that get put into your 10 liters. So that's your NHAO. So we're filling out the knowns from this system here for the pH, the charge system. So what else do we know? We know that there was no lactic acid at the beginning dissociated, so the NaO is going to be 0 moles. What else do we know? The KAP is going to be equal to 10 to the minus pKa of lactic acid times moles per liter times the volume. Now, pKa, that's going to be an extra that we need. So the pKa of lactic acid is what? Is 3.8 approximately. Yeah, look that up. 3.8. So that gives you the KAP. So we're filling out these knowns here. Then we're going to simplify, get rid of all the zeros that we have. So now if you're putting in the system a bunch of HAO, which way is a reaction that looks like this going to go? If HA is going back and forth to H plus A minus, which direction is this going to go? If you're adding a bunch of H plus and it goes HA and it goes out of equilibrium that way, then you're pushing it this way. So you're going to be consuming HA and generating H and A's. So that's generating, that's this one here. So this one you can delete because that's the reaction's going the other way from the assumptions that I make. So now we can simplify this. We need to make a solve block here where we put the guesses for all the unknowns that are in this system now. The unknowns are these: Hg, Hg, Ag, Hf, Af, because we're trying to find the final pH. How much C is consumed, HA is consumed, and how much HA final is going to be an unknown. So simplifying everything that's got zeros and getting rid of and plugging in. So let's copy these equations here, turn into this here. And I'm going to put one more constraint because it's nonlinear. There's more than one solution. So I'm going to constrain it so that the concentration of HF is greater than 0 moles. And now I'm going to solve. So then X is equal to, we're going to find, let's find the 6 unknowns here. NHO, the reason that's got an error is because this is too far down, so I need to move my box down here. There. So now my solution works. Okay, so now NHF is this first term. So to get the pH, we need to find out what that X at the 0 position is. That's the answer here. Then if we take that and we can find the concentration of H's, final is going to be this value here divided by the volume. So we know that's the concentration. Let's do it in moles per liter here. All right. So that's making you guess there that the pH is going to be somewhere about 3 something, right? Because that's 10 to the minus 6 times 10 to the minus 3. So the pH is going to be equal to the minus the log of that H concentration. But I need to divide that H concentration by moles per liter so that I cancel out these and get just this number, 0.06. It's go here, that's equal to 2. Oh, it's 2.0. Okay, so yeah, 0.006, 0.001 would be a pH of 3. So even bigger than that is going to be even a lower pH, so 2.2. So the pH of 2.2. So now how do you figure out the energy that you need to cool the system from 25 to 4 degrees C? That's just this energy system here that's closed, non-reactive, but dynamic. So you're going to have a box that's got a Q coming out, but no energy, so if you remember the energy system for a closed dynamic system, remember it's the m dot times EPI plus EKI plus HI minus m dot EPJ plus EKJ plus HJ plus Q dot, undo that, plus W dot is equal to the DE total dt, but you can change this into d the EP change of the system, the kinetic energy plus the internal energy of the system. And if we say that it's closed, then this term goes to 0, and this term goes to 0. And if there's no work, this is going to go to 0. If there's no potential or kinetic energy changes, that we're going to assume those are negligible, then those are 0. So you end up with basically that the Q dot is going to be equal to du dt, where if you remember the du, you can find as the mass of the system times the heat capacity of the system times the dt. So in this case, the dt is going to be here. If we're going from 25 degrees C to 4 degrees C over 30 minutes, we can sub in for dt can basically be T1 minus T2 is the dt, and the d to capital T, and the dt here is 30 minutes. Then this Q dot, MSIS is going to be, MSIS is the 10, or is the volume times the density, where density is, we're assuming this is just fluid in the, so we're going to call it density of approximately 1 gram per ml. This net mass of the system, so this is the mass of the water inside the bioreactor, is this mass. CP is something that we have to look up. We can assume it's close to water, so extra data is CP is equal to 1 cal per kilogram Kelvin. That's the CP of water. And so then we can come in here and replace this with Q dot equals this. So then in the end, Q dot is equal to, there's your answer. So we got the energy, we got the pH, and we got the time to stop the culture at the peak of the bacteria curve here at 23 to 24 days there.